Thank you very much. Thank you for having me here. I really appreciate that, and thank you everybody for being here. So I'm the last man standing here talking about corneal biomechanics. Sounds boring topic, but it's quite important, as they said, what do you mean by corneal biomechanics? Well, corneal biomechanics means that whatever the external physiological or non-physiological stress does to the cornea. Now, what do you mean by physiological stress? Physiological stress means intraocular pressure, your lid blinking, and non-physiological stress like keratoconus, refractive surgery, cataract surgery, thin cornea, scarred cornea, glaucoma, etc., etc. So why clinically these things are important? Well, we know that certain times we have a normal topography, go ahead with the LASIK surgery, end up with post-LASIK ectasia. Everything was normal, but still you end up with ectasia. A lot of time you have surgery, uncomplicated cataract surgery, your surgically induced astigmatism is way beyond than what normally you used to get. The identification of risk of glaucoma, we still don't know. Certain discs behave differently and certain discs are quite resistant. We don't know whether there are any risk factor for potential ectasia in certain cornea which may look different in the shape. Also, how the cross-linking behaves. All these things boils down to the study of biomechanics. When we talk about biomechanics, we talk about elasticity of the tissue. And we talk about elasticity, this is nothing but the ratio between stress and strain. What do you mean by stress and strain? Well, stress, think about a rubber band. You stretch a rubber band. When you pull the rubber band, the force which you are applying is stress. The amount of rubber band which becomes longer is strain. The ratio between them is the elasticity. Now, as you can imagine, if the force required is too high and it does not move forward, that means this ratio is quite high. And this is nothing but Young's modulus. What we call Young's modulus is basically describing the stiffness or resistancy to deform, and that's Young's modulus. Hence, if the Young's modulus is high, this is quite resilient material. Now we talk about these kind of things when we come to the cornea. Cornea is a little different. It has different elasticity in different zones of cornea and different sides of cornea, different layers of the cornea. If you look at the surface of the cornea, radially, in the central and paracentral region, it has meridionally very high modulus. Whereas if you go near the limbus, it is high modulus in the circumferential manner. Same way, if you look at the layers of the cornea, anterior 200 micron is different, it's much more stiffer. Middle 200 micron is little less, and the posterior 200 micron are, the fibers are not as strong as the anterior one. Now, normally when we talk about the stress and strain relationship, that means the amount of stretch you put on the rubber band, the same amount it will come out, and when you leave it, it will come back to the normal. That's the elasticity. But you think about if you stretch the rubber band too much, it's not going to come back to the normal. So, when we talk about the linear relationship of this thing, at one point of time, it loses that linearity and it does not come back to the normal. And it comes probably very slowly to the normal level or may not come to the normal level. And that brings us to the concept of viscosity. The viscosity means when anything which you deform does not come back to the previous shape or it takes really long time to come to the previous shape. And precisely this is what cornea is. Cornea is a viscoelastic material. So when you deform cornea, when you press the cornea down, you deform it, you see it will get deformed, and when you release the pressure, it may not bounce back as fast as you have deformed the cornea. The difference between these two is called corneal hysteresis. So the hysteresis depends upon the biological material, not only just biological material, but how the biological material is placed with each other. So that changes the property in cornea in different layer, because we know the lattice placement of collagen fiber is different in different layer of the cornea. Also, the relationship changes with the amount of stress you give. So rubber band, if you stretch a little less, well, it's going to come back to the original shape little slowly, but if you stretch too much, it's going to take a long time. So same thing for the cornea. When you talk about the biomechanical changes, the hysteresis value changes with the amount of stress which you give to the cornea. So how do we measure corneal biomechanics? There are certain methods like ex vivo method, which are laboratory methods, and in vivo methods, which we use it in patients. Lab method, the commonest use and earliest use was actually measuring the tensile strength of the cornea or cohesive strength of the cornea. Simple thing like experiment like this thing where you try to stretch the flap of cornea or flap of LASIK and find out how easily you can peel it off will tell you how strong the flap is. And we know from the studies that once you cut the flap, it loses its strength permanently and it may not come back to the normal level or the untreated area. In vivo methods are also plenty. They started with something like elastography, which was reported by Ford and colleagues, and which was probably not so famous. Also, shear wave propagation by using the high-speed ultrasound technique was also reported, which is quite simple. What they assume is that if you throw a stone into lake, it's going to create ripples there. Now, if you fill up the lake, instead of water with some different fluid, like say oil or something, the amount of ripples which will generate will be different. So if you keep the force same, but the amount of ripples which are going to generate different, based on that you can actually know about the strength of the material. And that's the plain concept of high-speed ultrasound. But the technique which shows quite significant promise is brilliant optical microscope. Now all these material, all these methods, what we talk about, we artificially generated stress there, and then we are trying to assess the biomechanical changes. But in brilliant microscopy, we are not doing anything to cornea, but we are just passing the photons from the cornea. An amount of scattered photons lead to, based on that, they calculate the property of the cornea. Now, we also know that when we have the availability of the refractive indices and the material and those things, this was 7 minutes, okay. So you can actually know about the biomechanical strength of the cornea. Finally, we have something called mathematical modeling. Now, this is something which is the cutting edge science, where you do not need to put anything there, but basically based on your mathematical data, you can actually calculate how strong the cornea is. As you can see here, advanced keratoconus, you can actually have a model of advanced keratoconus. You can have model of different things. You can have a reverse model based on whatever biomechanical property you have. Clinically, we have instruments like ocular response analyzer, Corvus ST from Oculus, which tells you, I'll try to wind up as early as possible. The Corvus is clinically much better than ORA, which gives you something called deformation amplitude. More the deformed cornea, weaker the cornea is. But how reliable and repeatable these are, very difficult to say. Clinically, where do we put this thing? If we calculate LASIK versus PRK in terms of biomechanics, we can see that the LASIK anterior stoma at least is much weaker compared to PRK. If we compare LASIK versus SMILE, but though ORA data did not show any changes, but when we see the mathematical model, we do know that at least the posterior stoma of LASIK is much weaker than SMILE. Same way, the elastography or the elasticity of cornea can be assessed by cross-linking. I'm done. To conclude, the study of biomechanics of the cornea would answer a lot of things: cornea at risk, disc at risk, surgically induced astigmatism, glaucoma. Clinically, there are a couple of methods, but the future lies in mathematical modeling as well as the brilliant microscopy. Corneal biomechanics reduced post-operatively with refractive surgery, maximum being PRK, SMILE, and then LASIK. I would like to acknowledge Rohit, Nandini, Natasha, and Abhijit for the presentation. Thank you.